Yes. Okay, good afternoon, everyone. Welcome to another Safari Live seminar. Today, it's my pleasure to introduce Dr. Konstantina Koliogeorgi. Konstantina received her PhD degree in 2023 at National Technical University of Athens, where she is currently a postdoctoral researcher at MicroLab Group. Her research has focused on hardware-software co-design, efficient high-level synthesis optimization, and design space exploration, targeting mainly genome analysis applications. So, Konstantina, thanks a lot, and feel free to start whenever.
So, thank you for the introduction. So, thank you for having me here. I'm really happy to meet you all in person. So the talk today is going to cover some of my major contributions during my thesis, and it will focus on software hardware co-design and data flow acceleration for short-read alignment. It won't change. So at first, I'm going to start with an introduction into the genome analysis and read alignment and provide some motivation behind the need to accelerate these applications. I then move on to present my two major frameworks that I developed during my thesis. The first one is an accelerator that is based on the data flow computing model and focuses on accelerating Smith-Waterman and integrating it into an aligner. And the second framework has to do with profile-driven acceleration for short-read alignment. I then move on to present some of my research ideas for the future. So, during the advancements in sequencing and molecular technologies, there has been an exponential growth in data that are known as omic data. Genomics, transcriptomics, proteomics, and metabolomics have presented an exponential data growth, and their enormous volume, as well as their heterogeneity, their complexity, and their unstructured nature, pose a real challenge in order to properly manipulate them. So as it is this challenging to infer some useful conclusions from this data and extract value, there is a need to develop some really complex analytics in order to manage to extract some meaningful associations, for example, associated with human phenotype. At the heart of this analytics is a genome analysis. So multiple applications have been developed that studies the genome in order to understand the genomic diversity, find some abnormal manifestation of genes, as well as even assist in drug discovery. Such applications are genotyping, metagenomics, epigenetics, genome editing, and pharmacogenomics. One of the ultimate goals of this domain is to revolutionize healthcare by providing some services to people, such as personalized medicine. Now, genome analysis is really challenging. One of the main reasons for that is the enormous volume of data. The volume of data has been attributed, of course, to the quick reduction of the cost of the sequencing. Now, both the cost of sequencing as well as the rhythm at which this data growth occurs, in fact, outpaces even Moore's law, which makes it very difficult for the computing power we now have available to cope with this volume of data. Essentially, the problem is that data are generated much faster than they can be analyzed. At the same time, applications have really strict requirements. For example, the trend is toward managing to work on this data on, for example, embedded devices, which means that there are some seriously strict source requirements, as well as that it should operate in real-time analysis. For example, the upper goal would be to eventually use this analysis to help in clinical practice. Therefore, it's evident that we need to do something to accelerate genome analysis. Now, in a typical, let's say, straightforward genome analysis pipeline, we have at least these three steps of sequencing, alignment, and variant calling. During sequencing, we have some machines that are called sequencers, and that they utilize the DNA sample and they manage to extract the sequence of bases of the DNA from this machine. These are called the reads. There are millions of fragments of DNA, and depending on the technology, they vary in length. Next, we have the read alignment step. In read alignment, essentially, we reconstruct the genome from the reads that have been previously generated by mapping its read in a location in the reference genome that is most likely its origin. Lastly, we have a step of variant calling that locates the differences between the restructured and the reference genome. Now, in this pipeline, it is very common for the bottleneck to lie in the second stage of the alignment. Read alignment can be a major bottleneck and can take up even 60% of the execution time, as can be seen in various studies and works. For that purpose, and this bottleneck is attributed to multiple factors. For example, it is located on the immense data volume of data. The dataset size of the reads is on its own really big, and it's even exacerbated more when there are analyses that have to operate in multiple species or across population. But even in order to align a single read, there are potentially many different locations on the genome, so this manages to put an exponential growth in the datasets. Also, each alignment task is on its own pretty complex, as it relies in very expensive approximate street magic operations. And lastly, we have also a bottleneck attributed to the data movement, as we have some costly data transfers from memory and storage. For that purpose, and since alignment is the bottleneck in this genomic analysis, in order to accelerate genome analysis, we often target the read alignment, and we have to develop some strategies that manage to alleviate these exact bottlenecks. So there are solutions that target the reduction of the number of tasks and the volume of data that we have to operate on, reduce the time for a single task, as well as minimize the data movement. So in this next slide, I present some, let's say, state-of-the-art approaches in order to accelerate genome analysis and read alignment. So we can target different functions within the alignment, for example, the indexing, the pre-alignment filters, the chaining, and the alignment itself. We can leverage different algorithms and heuristics to optimize the execution time, as well as leverage the potential and capabilities of different technologies. So for example, in the area of the cloud service, we have, for example, Azure and AWS, and we can accelerate some pipelines there. And some vendors such as NVIDIA and Illumina have actually developed some tool frames, such as the Dragon IT and the Parabricks to perform this analysis efficiently. Then we have the category of HPC devices. In this category, we have the development of accelerators, either for indexing, pre-alignment filters, or at the alignment step. And we target FPGA, ASIC, and GPU devices. And recently, there have been also many workflows or individual steps of the analysis accelerated with processing in memory or in storage. Now, my work actually focuses in the alignment stage, and specifically alignment of short reads, and also combines some knowledge and information coming from the pre-alignment filters. And the goal is to accelerate those on an FPGA accelerator. So in a sentence, I can say that my thesis focuses on FPGA acceleration of DNA sequence alignment based on high-level synthesis tools. There are three major areas of interest and focus that come from my work, and this has to do with the data flow computing, an integration of our software hardware co-design, and lastly, a profile-driven design methodology. The first work I will present is a high throughput accelerator for short read alignment that includes a data flow accelerator for the Smith-Waterman algorithm and the real system integration of this accelerator within both I2 aligner. The second work is a sort of an extension of the previous one, and it proposes a profile-driven methodology for the acceleration. It includes a data flow implementation of the Banded SmithWaterman accelerator that is customized to the eddy profile of input, as well as a dataset-specific multi-dataflow system. Let's start with the first framework. I have prepared here an executive summary to have an overview of what I'm going to present next. So as I mentioned before, genome analysis is bottlenecked by read mapping and read alignment, which is implemented usually with approximate string matching, such as a Smith-Waterman algorithm. Now, most works focus on accelerating the Smith-Waterman. However, they ignore some system-wide integration aspects into integrating this accelerator into a real aligner. Therefore, they ignore issues like the data transfer and communication overheads. The goal in this work is to provide high-performance acceleration for Smith-Waterman, but also for the end-to-end aligner tool. Therefore, I'm going to present this data flow acceleration framework that includes the data flow implementation for Smith-Waterman and the real system integration that is enabled through efficient hardware-software co-design, which in turn is enabled by two key architectural decisions. The first one is moving more computation on hardware, and the second one is performing some necessary source restructuring. And the results are very encouraging in comparison with other state-of-the-art aligners. So we mentioned before the main stages of a typical genomic pipeline. In this case, I'm going to focus on the short read alignment. Now, most aligners use the seed and extend model and dynamic programming algorithms such as Smith-Waterman to perform the seed extension phase. Smith-Waterman comprises of two stages, the matrix-fill and the traceback. Now, using a second framework, we have utilized and profiled several genomic analyses that include both type 2 aligner and different variant colors such as free Bayes, same tools, and GATK. We can see that most of these pipelines, both type 2 was indeed the bottleneck. Now, by further profiling both type 2, we can see that the bottleneck indeed comes from the Smith-Waterman, by large part by the matrix-fill and then by traceback. Therefore, the goal will be to accelerate the Smith-Waterman and then integrate Smith-Waterman into both type 2 aligner after doing any necessary modifications.
Sorry, what is the other part?
This one?
No, 40% other. So is this related to FM index, BWT?
Yes, FM index, yes.
So is it fully like the FM index or BWT is consuming 40% of that other?
It doesn't include the creation of the index.
I see.
It's only the search part, the seed.
Have you looked at it? So not necessarily creation, but querying, let's say.
How it performs it.
Exactly. So what is that percentage over here?
I don't know the exact percentage, but I remember from my profiling that it wasn't really dominant. Like I didn't really even target it for acceleration because this 40%, it was distributed in really small percentages, even less than 10%, if I remember correctly.
And all of them are different tasks.
Yes.
Other than...
Some of them I couldn't really understand what kind of operations they did, to be honest.
For example, does it include the I/O?
Yes. Yes, definitely I/O.
Konstantina, could you please repeat the questions because I'm not
Exactly.
sure.
Yes. So the first question was what this 40% includes, and if it includes the seeding step. And the other question had to do with if there are some I/O operations included in this one. So yes, it includes both the reading of the reads from the fast queue as well as some sort of reporting and statistics. The output of both type 2 aligner is actually a file that includes, I think, the cigar representations of the alignments.
Mm-hmm. So that's interesting because there are also some other accelerators that specifically target FM index acceleration, and they make these arguments. That's also a costly step.
Yeah, I know. I've seen that in literature too, but in this case, it was not a dominant.
So do you have any insights like when that becomes an issue?
When it becomes an issue?
The use of FM index.
Well, I understood that it was an issue before the FM index. So FM index actually accelerated this searching process. So in my mind, this bottleneck was resolved because they used in this both type 2 aligner a fast search.
I see. Okay.
So now I'm going to say a few words for this seed and extend model and how this is implemented in both type 2 aligner. So it works in two phases. The first phase, in the seeding phase, each read is fragmented into even smaller pieces that are called seeds. And then we search the genome for the exact matches of these seeds that are called seed hits. Both type 2 also implement some sort of prioritization of the seed hits to start looking first at the seeds that are more likely going to lead to a valid alignment. Then during the extension phase, we extend each of the seeds into some full alignments, allowing mismatches by using the Smith-Waterman algorithm. Now, what's really interesting to see here is that not all of the seeds are actually checked. Some of them are skipped based on the results of previous seed tries. And of course, there is a limit on the tries per read that the algorithm allows. In general, it is important to take note that for the alignment of each read, we have to invoke an unbound number of tasks for alignment, and that the chain and series in which the seeds are checked cannot be known a priori, but it is decided on the runtime. So now a few words for the Smith-Waterman accelerator. Smith-Waterman measures the similarities between two sequences using a score. The highest the score, the highest the similarity. So we have two stages. It's the matrix-fill and the traceback. During the matrix-fill, we fill in three matrices CFH, based on some equations. In order to fill up each cell, we have to rely and have data dependencies from the neighbors that are up left on the up left corner of the cell. It means that we have some anti-diagonal dependencies, and we can actually parallelize the completion of this matrix by using a sort of wavefront approach. Therefore, this matrix can be filled in as many steps as are the anti-diagonals. The traceback now starts its job from the cell with the highest score and starts traversing the array in reverse in order to reproduce the alignment. We can see here the example of an alignment that has a single gap in the read in order for the sequences to match, and this is called an edit. What's also important to take notice of here is that in case where we have a perfect alignment, an exact match, this alignment lies in a single diagonal of the original matrix, starting from the position of the seed heap. If we have some edits, then we start to deviate from this diagonal, and therefore we have to span across a larger and broader band of the matrix. So this is an overview of my design. I have implemented the accelerators, the kernels using the dataflow computing model, as this is available by Maxler Industries. So I have declared two different kernels, one from the matrix and one for the traceback operations. The matrix field computes the matrices CFH and the maximum score as a systolic array of processing elements, and sends back the data of the matrices in a reverse order for traceback. Traceback now reads the data in reverse and constructs the alignment. In order to achieve an efficient implementation of this, I have adopted like an interleaving data scheme for the input data, and I have employed a double buffering technique in order to allow for the matrix fill and traceback to operate in a pipeline. Now, some more details about the architecture. First, we have the matrix fill. This is implemented as a systolic array of processing elements. Each processing element is assigned one base of the query sequence, and the reference sequence flows through the array in order to create a row of the initial matrix. Now, all the PEs operate in parallel, and at any given step in time, we have the calculation of a single diagonal of the matrix. This is why we can see that we end up with a sort of skewed layout of the matrix. In order for this sort of anti-diagonal dependencies, in order to fill in this matrix, it takes as many steps as is the number of anti-diagonal times a latency that takes for a single cell to be calculated. Now, traceback starts receiving the anti-diagonals in reverse and starts from the point of the cell with the maximum score. It always waits up for the two previous, let's say, anti-diagonals to arrive and check if this is indeed the point of origin. And it only sends to the CPU some information about the edits regarding their location, their type, and what were the exact characters that were different one from another. Now, this is a view to the interleaving schema that I utilize for my datasets. So as mentioned before, each cell has a latency to be calculated. So in order to avoid any stored cycles, I utilize multiple read reference pairs and interleave them starting from the input. So I fill in a single buffer with my input data and place the bases from different pairs in a sort of a modular manner, actually like a modulo. And this interleaving schema is propagated to the intermediate data as well to the output. Lastly, I have enabled this double buffering technique. So due to the dependencies, the traceback needs to start operating from the from the end of the matrix. Therefore, it has to wait for the matrix fill to first fill all of the matrix. At the same time, the matrix fill shouldn't start writing on the array, since traceback may require this data. For that purpose, I have utilized two instances of each array and used an enable signal to change the privileges, the read-write privilege for the copies from the matrices between the matrix fill and traceback. This achieves the pipeline execution between the matrix fill and traceback in a way that traceback is in the end sort of overlapped with the previous matrix fill. So now that I have presented the architecture of the accelerator, we move on to the integration into the aligner. Now, there are some interesting results and implications when trying to integrate the accelerator. For example, the profiling reveals that the major bottleneck is actually the matrix fill. First, a more naive approach, which I followed, was to only accelerate the matrix fill. This would mean that I would have to send the matrices CFH back to the CPU, and I would have to pay a really huge overhead for the data transfer. For example, for these datasets, I would have to transfer 186 terabytes of data. In order to avoid that, we decided to move traceback also on the hardware. That way, I only have to return back the discovered edits for the reads, which is only, it cuts down the data that I have to transfer to 5 gigabytes, achieving a really impressive compression rate. Still, however, there are some other implications that have to do with the nature of how botai2 is written. If we profile, we can see that for each read, botai2 can actually do 1 to 170 tries for alignment. So even if it only had a single try per read, if we want to align a 60 million read dataset, we would have to invoke our accelerator 60 million times. Now, depending on the technology, this would have a delay that could actually add up to days of computation. Therefore, we have to find a way to constrain this number of the accelerator cores. So now we move on to the modifications I performed in botai2 aligner. The goal is to create some batches of candidate alignments that can be aligned during a single accelerator call. So I modified the source code so that it can operate in 3 distinct phases. The first one is a data gathering phase. What I do here is create first a batch of candidates from a predefined number of reads. For each read, I have to inflict a limit of maximum tries per read. Then I rearrange in a buffer this input so that they can operate in the interleaving manner that is expected from the accelerator. I then move on to the stage of the hardware run that actually runs the accelerator on the hardware and the alignment. And lastly, the data distribution phase that gets the edits and the differences between the sequences back and does some reporting and constructing the output files for the alignment. So now we move on to the experimental setup. So I have completed all the experiments on an Intel Xeon processor that is connected to a machine and a workstation available by Maxeler. This workstation includes 2 ultra-scale FPGAs. They're connected through PCIe, and the on-chip SRAM is 38 megabytes. I have created my accelerators using the Max compiler available through Maxeler that incorporates for the part of synthesis the Vivado framework. In terms of genomic data, I had used the latest genome reference available at that point, and I have used both simulated and realistic datasets. The simulated datasets, I utilized the MIG simulator, and I created datasets of different lengths, 50, 100, and 150, with 20 times coverage and an error rate according to the error rates available by Illumina for short reads. And the next dataset was one that was actually acquired in a clinic, and it referred to patients that were suffering from the CLL disease. So moving on to the evaluation, first I'm going to evaluate the accelerator as it runs on its own without the integration domain. So I have compared it with different state-of-the-art software and hardware aligners. For the software aligners, I have selected the ADLib, WFA, KSW2, the software version of GENAS, as well as the BOTI2 SIMD optimized Smith-Waterman. For the hardware comparisons, I utilize an open source dataflow implementation of MicroLab that only implements the matrix-fill and the traceback, and then the GCT accelerator from the Darwin paper. I compare these designs using the throughput that is defined as the number of alignments found per second. And I run this on the Intel Xeon processor and with a hardware accelerator. As a target for the hardware accelerators, I utilize the ultrascale. So I can say that my design is faster than all software implementations. The fastest one is ADLib in these measurements. And my design manages to score around 2 times faster than GCT. In order, however, to be fair and not only compare a single instance of my accelerators with the other hardware accelerators, I have also performed a comparison between the hardware accelerators that I try to instantiate as many accelerators as possible on the FPGA device without, however, compromising and dropping the frequency. So for my design, I have managed to fit 3 Smith-Waterman accelerators with a frequency of 200 megahertz. For the GCT, I have managed to fit 25 computing units at 150 megahertz. And for the MicroLab solution, 14 Smith-Waterman accelerators. And we can see that my design manages to outperform MicroLab by 9 times and the GCT by almost by 5.5 times.
I have a question. So is the leftmost point is GENASM?
Yes.
So I think this is quite a significant speed up. Do you have, I guess, ideas where, let's say, source of speed up is coming from compared to GENASM?
I'm not sure why this is and why GENASM performs worse than other software aligners. I didn't do any fine tuning. Like there must be maybe some configuration for sizes in GENASM that could maybe favor it better, but I didn't do any, let's say, tuning of parameters in this case.
So have you utilized HBM over there then?
No.
I see.
This is the CPU version of GENASM, right?
Yes, it's a CPU.
And the comparison point is the CPU version of GANDAFL, or?
No, it's with a hardware accelerator.
Okay, with the accelerator and CPU version of GENASM.
Mm-hmm.
But why not FPGA version of GENASM?
It wasn't I couldn't implement it. It wasn't open source to implement it. But however, from like measurements mentioned in papers, I would expect that GENASM would be around 2 times faster than my design. That I inferred because I remember that in GENASM paper, there is a comparison with the ASAP accelerator. And I think it mentioned there that it was 4 times faster.
Mm-hmm.
And by some sort of spreadsheet analysis of my own, I expected for my design to be 2 times faster. So for the hardware, I'm definitely slow.
But then also you're not benefiting from HBM or whatever. So maybe if you had, okay.
But I'm benefiting from this data flow because I get to overlap a lot of my transferring data with computation.
And did you also try to measure the execution time of WFA on the FPGA?
No.
This is a CPU version of WDF.
Yes, it's everything is a CPU except for the MaxLearn and GCT and my design.
Do you expect that to see better results with higher memory bandwidths?
Well, it could definitely transfer data faster, but to be honest, at this point, I think that because of this overlapping of computation, I won't see any significant difference. And also, because I have accelerated the alignment part, in the end, especially in the integrated design, which I'm not there yet, however, the time has dropped so much that further acceleration will not show anything else, according to the Emdal law. Okay. So now we move on to the integrated design. And first, I'm going to evaluate the accuracy because, as I mentioned before, I do inflict a limit for the number of tries I allow for each read to perform. However, despite this, let's say, restriction, I have a rather small accuracy loss of like 1%. So if we notice the histogram that shows the number of tries for each read, we can see that the majority of the reads get, for these data sets, around 8 tries. However, even for most of the reported alignments lie within the first tries. So even there is a read that performs more than 8 tries for alignment, this alignment is not going to be the, let's say, the optimal one, the one that is going to be reported. So for that reason, I don't experience any accuracy loss, important at least. So now regarding the performance when integrating my accelerator, I integrate a single accelerator in both type 2 with a length of reads for 100. So therefore my P's are also 100. And the frequency is 200 megahertz. I compare and I measure for 3 different two data sets. As for the first one, I acquire a speed up of 1.92, which is actually pretty close to the optimal as indicated by the Emdal law. It's 1.96. For the second dataset, however, I only acquire 1.26 speed up compared to the 1.67 indicated by Emdal law. The reason for that has to do with the dataset. This is the one that has been actually manipulated by clinicians. In this case, there are fewer tries per read in the software version. So each read makes like 3 tries around the mean. Let's say the mean is 3 times checks per read. However, in my design, I have fixed this value to 8. Therefore, I perform more computation both in the hardware as well as some increase in the software manipulations of data. As you can see in the gray column, it has increased from the original one. So this is why I have not yielded the maximum speed up.
What was the read length for this data set?
It's 100. And lastly, in order to also be fair and also evaluate some multi-threaded implementations, I have utilized the multi-threaded BODI2 and performed an experiment for an accelerator sharing scenario where I utilized 2 of my accelerators, one in a different FPGA, and I scaled the number of threads so that the threads can share the accelerators. And we can see that the design and this way of scheduling performs well. And I even go from speed up of 1.73 to 3 times speed up when utilizing 48 threads, that they also are the same to accelerators.
Why do you need to associate them with 2 FPGAs? Because in the previous slide, you were associating many accelerators in a single FPGA, and you could fit like 3 of them in maintaining 200 megahertz.
So the workstation that I have available has 2 separate FPGAs. So this is the ones I utilize here. But I instantiate a single accelerator per FPGA in this case.
Okay.
Previously, what you saw was 3 Smith-Waterman accelerators within the same FPGA. Here, I didn't utilize all 3 of them because it's the integrated scenario, which, as I said before, by using, let's say, 6 accelerators, I didn't get any more end-to-end speed up than using 1 per
FPGA.
because of the interlock.
Okay.
Why not using 2 instances of the accelerator on a single FPGA?
Because I would have 2 threads that are fighting, they couldn't program at the same time as an FPGA.
Okay, so the problem is
It has to do with how Maxeller's framework works. Each time I have to basically put a lock on the device, something like that. So there are some machines of Maxeller that had like 8 FPGAs available, but I didn't have access to them.
So you cannot access at the same time with the FPGA chip.
Yes, because they're different FPGAs, so I can access them at the same time, but not 2 accelerators in the same FPGA. Unless it's the same thread process that does the request. But even then, I would have to have a single function that calls accelerator and send the data at the same time, not in different timings.
So apparently Volta is not benefiting from more threads after 32, right? Because there is a slowdown for Volta. And I
That
guess
it
yours-
slows down.
Yes.
Yes.
Increases. And I guess your speed up is a bit lower than 1.73, right, until 32 threads. Based on difference, I guess, between software and so.
This,
did you look
however,
at,
I don't think, because when I measured the Volta on its own and scaling the threads, I didn't really see any sort of plateau. In this case, maybe it has to do with too many threads fighting for the accelerators. Maybe there was some increased their requirements. Because the accelerators are only 2 devices. So maybe there was some delays for 48 threads to do this.
so is there an accelerator for software on Volta as well?
No, it's not. Yeah, you're right.
So did you look at why there is a slowdown or?
No,
you are
I
not
don't
there?
remember looking into it actually.
How many cores do you have in your system?
How many cores are there? I don't really remember the specs right now.
You can discuss it.
Yes, I can look it up, maybe in my paper I mentioned it. So actually, if there are no questions, can I move on to the next framework? Okay.
So I just wanted to discuss one more thing.
Yes.
So that's probably more like a brainstorming topic. First, like, do you know how much a memory needed when basically you're utilizing traceback as well in alignment? Did you measure basically the size of your DP tables and so on? And I guess
Yes.
this causes probably higher power usage and also high memory usage, right? And is this limiting your, I guess?
Yes, this is
number
the
of
limiting
needs?
factor in my
Okay.
design. It's the bottleneck. So for a single instance of my design, because I actually store the matrices, the EFH, I store them for the
Exactly.
traceback to go back. So with a single instance, I use up like 23% of the block RAMs. This is the limiting factor in my design. So this is why I can only fit 3 designs, because if I increase it, then the frequency really, I think I have managed to fit 4 accelerators, but the frequency drops to like 65 megahertz.
So also, like, did you check, or, so there are basically these optimizations that disable traceback. So there are certain applications that really don't need traceback, but rather fills the DP table just to get the final score from DP. And since you don't need the basically traceback functionality, they don't have to store the entire DP table. Actually, you only need to store, let's say, the last row.
You mean that the application by default does not need to do the traceback at all?
Yes.
Okay.
And so by like that, I would be curious if you looked at these optimizations. And second, maybe like there's something there, like where you first perform matrix fill operations, right, without traceback, so you only fill, and you do it again, matrix fill plus traceback, only if basically alignment is promising enough. Meaning you have a good score, so you may think that, okay, so I need a traceback for this because this is clearly aligning, something like that. So what do you think about?
So for the first part of the question, indeed, I have some designs where I exclude the traceback, and my design scales much better. Like I can fit 16 matrix fields.
Okay.
So this is definitely true. However, at that point, I didn't have in mind an application that was like, I don't need the traceback. So for me, at that point, it was necessary to do the traceback. And for that, I think I have read some papers at that point that didn't do the traceback and only said do it in the software domain. I did the traceback to enable this integration.
Yeah, of course.
Yeah. So, but I understand this point of view, and I've seen it also in papers. And
maybe you don't have to do it every time. Let's say you look at matrix and you say it's not a good alignment, so let's not do traceback at all. And if this, let's say, promising, you redo matrix fill.
However, in like in such data sets that are like short reads and highly accurate, is it worth it to do that, or most of them are good alignments?
I guess that depends on the sample you're looking at. If there are too many mutations, right, you may expect still some edits, I guess.
Okay.
So rather than the sequencing error, I guess the concern over there are those mutations.
This reminds me of some like filtering approaches that I've seen in also in some of the group's paper. So wouldn't these alignments, could be they filter at the previous stage before trying the alignment at all? Or sometimes it's only evident in the matrix fill stage?
I guess it depends on how, so do you have a number, how many times you're rejecting an alignment? So it really completely depends on that, right? So you do the alignment, but it's not aligned. So if that ratio is relatively high, there may be something there.
Okay, that's interesting.
Yeah.
It really depends on the seeding mechanism as well.
That's all.
I mean, depending on the seeding mechanism, there might be false alignments, let's say false candidate alignments, and then that's like getting rid of those alignments might actually work. Related to that, I actually have another question. So for each read, for example, I guess you mentioned something like you consider like more than one reference segments, more than one candidate reference segments. So do you, for example, keep these matrices simultaneously for each execution, for example?
Yes, so I have, at this point, I have changed the source code of what I do. So for a predefined number of reads, I do save them and store them. However, yes, the order in which these are, if I let the software run like one by one the seeds, I think that sometimes the order in which the seeds were checked would change in comparison to what I do, because I have to store them when they're discovered.
Yeah, because for each of the alignment, I guess you're doing a find get not like model because you're keeping 3 matrices, right? So there are E, F, and G, I guess, like in the system. Those should, in my opinion, should like account account for the affine model matrices. So there are like 4 matrices for each of the alignments, right? And for example, depending on the read length or depending on the load of the execution, do you have a predefined number, or like during the execution, you just calculate the amount of, let's say, number of reference segments per, let's say, execution, and then go for it?
So in this work, I have fixed this number to 8. However, this can be decided like it's in the software side, so it can be easily reconfigured and then offloaded to the accelerator. And then another work after this, I also tried to actually play with this value. And for example, at the very least, try not to, for some reads that they would be fine with less than 8, I only send the lesser number. But I didn't get any impressive results and changes in the performance, at least.
So basically, 8 is like an experimental number that you got with the optimal results.
Yes, I did some histograms and I found out that like majority was performed around 8. And it's what I mentioned about that the reporting alignment lie within this 8 limit. Move on. So now I'm going to move on to the next framework that I have developed. So as I mentioned also in the start briefly, we can see that there are 2 approaches in accelerating the alignment. The first one on the right is the approach that targets the acceleration of a single alignment task. This is usually implemented by developing accelerators, for example, for FPGAs, GPUs, such as is the Darwin, GENAS, GENX. Another solution would be, however, to try and limit the volume of tasks that we have at hand and avoid some needless extensions. And of course, even for this, we can further accelerate it with accelerators. So this is utilized with the pre-alignment algorithms that manage to, for example, discard any alignments that do not fit some predefined threshold for accuracy. So in this next work, I take account of these 2 approaches. The first one is completely data aware, as the output depends on the input. However, the second one is data agnostic. I therefore here try to bridge these 2 approaches, and I combine some pre-alignment that happens in the software with a hardware alignment accelerator. And I try to leverage the information from the pre-filtering to customize my hardware design. So I present a profile-driven methodology that is customized to the input edit profile, data flow accelerator for Banded Smith-Waterman, and then a multi-accelerator designs that includes accelerators of different edit thresholds. So to better explain this, I profile 3 different sets of datasets. The 2 are the same as before. However, I also utilize a sample from the Human Genome Project. And I studied the histogram of the number of edits for all the alignments that occur within this dataset. And what I can see is that for 70 to 80% of the alignments that occur, most of them only have a single difference with the reference. And 99.99% are okay with exhibit 18 edits. So there are 2 important insights from this. The first one has to do with the fact that the edit number can actually affect the size of the accelerator. As we can see in the figure, the distance from the C diagonal has to do with the number of edits that can be found. So the smaller the edit distance, the narrower the band in the matrices is. Therefore, we can exploit the Banded Smith-Waterman algorithm that by default only searches within this band and create some light size accelerators that are customized to the edit threshold. Now, the second insight has to do with the frequency in which each threshold occurs rather than the threshold value itself. So if we look into it, we would see that this distribution for the edit threshold actually translates into a distribution for the time taken by each type of alignment. So we would have a better system if we could instantiate multiple smaller size accelerators with different edit thresholds, compliant to this edit distribution, rather than a generic one that is of greater size. Simply put, we need more accelerators for the edit thresholds that most frequently occur. I also have prepared like 2 motivational examples for this purpose. Assuming we have an alignment task of a data set and we can deploy generic parallel accelerators that work in parallel. In this case, we would have a speed up of at most k. However, what we propose here is that we look into our data set and find some dominant edit thresholds. And let's say in this case that we have 3 edit thresholds that are most dominant, E1, E2, and E3. And then we utilize 3 different kinds of accelerators that are smaller than the original one, that are customized to the edit threshold and distribution. So we would instantiate K1 accelerators that are larger in number because they would target their alignments with the edit threshold of E1. And same goes for K2 and K3 accelerators. Therefore, this way we could instantiate in total more accelerators than K and have a greater speed up. So this is the major idea, and I have also formulated a model.
Konstantina,
Yes.
maybe one question. But I guess you're not directly, let's say, running the T2 accelerator, right, before running T1. So I would imagine you first, let's say, run like whatever the fastest is, right, and then somehow figure out that read is not really fitting to that accelerator because probably higher number of edits. So then you go and run the second, I guess, more sensitive that can, I guess, tolerate more edits and so on. So basically my question is, do you do something like first, I guess, run T1 and then second try is T1 plus T2 and the third try is T1 plus
No,
T2?
that's not. The idea is that these actually run in parallel. And the reads first pass through a filter. Later on, I will mention that I use Sneaky Snake as a filter to find its alignment with how many edits is, let's say, accurate enough. And then I assign it to the Banded Smith-Waterman accelerator. So in this example, however, I assume that I know that it's read how many edits there are, it goes to the correct accelerator, and this happens in parallel. So this is the assumption here.
So you're scheduling the read inside the correct accelerator, but okay, so the filter is the one doing the scheduling. And is the filter providing this feature natively, or you support it? I mean, you natively.
But that's really the ideal case, right? Like you always schedule to the right correct accelerator.
Yes, at this point, I think yes, it is.
And how accurate is this the ideal case? I will look at it. Like, are you always basically scheduling to the right accelerator?
Yes.
Okay. So you don't really have those.
Well, as the reads are found, I pass them through the Sneaky Snake, and they find the threshold for each of those. So, yes. Now, in the second scenario, I have include like a model scenario that I assume that my data set has this distribution for the edits and the time, 70, 20, 10%. I assume that all accelerators have equal speed up, but they show some fractionally smaller area utilization. And I plot here a diagram that shows that for the same resource utilization, I can always find the configuration for the smaller, lighter size accelerators that performs better than instantiating the generic homogeneous ones. So now I present here the idea of my framework. So first I'm going to do a profiling find the edit distribution and the edit thresholds that are most dominant, and then fix and create as many edit customized Banded Smith-Waterman accelerators as indicated by the thresholds. Then through a pre-filtering with Sneaky Snake, I would decide if the alignment can be done with a given edit threshold and classify the alignment to the suitable Banded Smith-Waterman accelerator. And then we have the component of the accelerator architecture that comprises of multiple dataflow accelerators that follow in numbers the distribution for the edit threshold. So this is the architecture. And now some details for the implementation. Again, here I have utilized the systolic array processing elements. However, this time, I only have to focus on the band size, which includes the seed diagonal and as many upper and lower diagonals as indicated by the edit threshold. In order to do that, this gives me the opportunity to not store the entire matrix, but rather only the band area of the matrix. So therefore, even though I compute the whole matrix, each time I use some sort of mask to sift through the cells that are actually of interest, and I store only those. So this really helps me to minimize the resources and alleviate the bottleneck that I mentioned in the previous accelerator. This way I can fit much more Banded Smith-Waterman accelerators on the FPGA. Traceback is implemented pretty much the same way, only this time it only receives the band vectors, and it is implemented as some sort of state machine. As input, it has an indication of which matrix it should look up into, the index of the band, the index of the reading reference, and it simultaneously checks all possible origins and uses some sort of one-hot encoding selector to choose which one is going to be the next state and search in the path of the alignment. So now moving on to the experimental evaluation. I have used the same setup as before. The additional tools I use is the Sneaky Snake pre-alignment software version and the new dataset that comes from the Human Genome project. First, I'm going to evaluate how well the accuracy when integrating Sneaky Snake with the Banded Smith-Waterman implementation and compare it to a reference of both I2. So range the number of the edit threshold and can see that indeed after increasing the edit threshold over some point, I think here it's 10, I can get the same sequence as is found by the reference. The sequence, the same accuracy, sorry.
Is that edit threshold or read length?
It's edit threshold.
It's 150.
Sorry. Yes.
Read.
It was the default in the software. I don't believe it reaches it.
Did you try also to use this Snake FPGA accelerator? Did you try to connect?
No.
Do you think it would benefit your performance, your overall results?
Of course, because I think it would, because it was going to be like an end-to-end workflow. But yes, at that point, I think I didn't have time to do like the data flow implementation for the Sneaky Snake.
I also have another question. Could you go back to the previous slides, the one with the distribution?
Sorry, which one?
One more, yes. Yeah, this one. Next one. Okay, thank you. So you created that profiling and created a distribution, okay? And that depends on the specific data set you have, right?
Yes.
Okay. So when you change your data set, you'll have to change how you instantiate those accelerators on the FPGA, right?
Yes, in principle, yes. What I found is that all these datasets that I utilize, they're short-read datasets, and they sort of have a very similar distribution. I'm not sure if this can be something generic for the short reads, for accurate short reads in general. But it would be interesting to find out an architecture that fits for a larger range of inputs.
All right.
This one is customized to the input indeed.
Okay, so you're telling that this one is actually quite, not saying optimal, but at least very good in working with different data sets, even if I don't have to reprogram the FPGA.
Sorry, can you repeat that?
I mean, the kind of layout we have, so the number of different size accelerators is performing very well with the different distributions, since with a different data set, the distribution is not changing a lot, right? This is the point.
Yes, however, in my experimental section for each data set, I have a different configuration for these accelerators.
Ah, okay. Okay.
But they're so close one with another that I think I would get the same results if I utilized the single architecture.
Okay.
However, I don't think that this would be the case for any data set. We would have to do further profiling, and this is actually something that I'm interested in, seeing how different inputs can impact.
So I'm actually quite not familiar with the design of these accelerators. But are they sharing common functional units such that you can kind of, build such a structure within basic FPGA that you can easily morph, to different configuration, changing some parameters?
So you mean if I could reuse the same module instantiated in hardware when it is free from one accelerator, that it could be utilized from another? Okay, that seems very efficient, but in this case, it's not happening. It's completely parallel instances of the accelerator.
And it's fully utilized.
Sorry?
So everything is fully utilized.
In ASIC, I guess I would have the freedom to do that.
Yeah, but the organization of different accelerators, it's meaningful on FPGA because you can easily reconfigure, right? But imagine that we have this accelerator on ASIC, such that we can easily reprogram, right?
Mm-hmm.
But still, it should be possible by changing some parameters to make larger accelerators or smaller accelerators, by combining some smaller accelerators to make a bigger accelerator.
Okay.
If you implement some functional units, compute engines, and combination of those compute engine can make different accelerators.
Okay.
Do you know what I mean? And
yes, but can you decide in the runtime which to utilize?
yes, it should be possible. No?
In that case, would some modules sometimes they would remain idle, or they would be utilized by other?
We should try our best to make everything utilized, but I'm not sure. This is a very raw idea, but I'm thinking of if these accelerators are sharing some common functional units, then it should be possible to make different accelerators runtime on ASIC, basically, not on FPGA.
Okay, so that would be good for the case where I have a single architecture.
Mm-hmm.
And so in case that I have some read length and edit errors, and some of them remain idle, they can be actually utilized by the others that suddenly become more dominant.
Yeah.
Okay, that would be indeed very good. Another interesting thing would be, I guess, to maybe if you could combine the smaller ones to the bigger, unless you said that.
Yes.
That's to do the same operation, you mean?
Yes, just saying the. So we have
like somehow combine the one that finds up to one threshold into one that finds, let's say, two. Okay.
So is there any difference between this picture E3 and the accelerator in E3 and the accelerator in E4?
Now this figure is actually it doesn't mean something. Supposedly, E3 can find alignments with at most 3 edits, and the other one at most 4. But in size, I guess they look the same.
but architecturally, when you look at what's inside them, they're different.
Yes, the one that finds more edits should be sort of larger in size. However, in this specific implementation, I didn't see a really impressive scaling. Like up until a really big edit threshold, I had pretty much the same utilization. Yes, so now regarding the evaluation, first I have evaluated again the single instance of my accelerator. I have compared it first on the above figure with only software aligners. And on the figure below, I have performed the comparison with the hardware aligners, again with my previous design in GCT. And I can see that now I'm 3 times faster than GCT and 1.5 times faster than my previous implementation. This speed up concerning my implementation has to do mainly with the fact that in this implementation, I managed to acquire a clock of 400 megahertz. So it's only attributed to the clock rather than the design. And now moving on again by instantiating as many hardware accelerators as they fit on the device. For GCT again, I have this. I made an exploration and synthesized, and I have managed to fit 25 instances with 120 piece. For my case, for the previous framework I showed, I managed to fit the 3 instances, and in that case right now, I managed to fit 8 of them. And I acquire a speed up that is almost 5 times faster for my comparison with my previous work, and almost 25 times faster from GCT. So now we move on.
I have one question. Am I reading the figures correct? So GANDAFL.
Yeah, I don't even say it. It was a bad choice.
In the second figure, you have an alignment per second of 0.6 or 7, something.
Sorry, it's a power of. It's like 10 in the power of 6.
Yeah. But do you have the same number in the third figure as well?
Yes.
So when you have one GANDAFL.
Sorry. You mean the same absolute value? No, they shouldn't be the same absolute.
But they're very similar, I guess, right? So that it doesn't scale much with multiple instances.
Okay. I don't remember the exact. Okay, I don't remember the exact number, and I don't know why I didn't really. I mean, I would have noticed it. I can look into it.
Okay.
And also in the first figure, the proposed one is also the software baseline or the hardware?
It's the hardware.
So the last one is the last one on the right is actually using the 8 instances for the proposed solution.
Sorry, it uses?
It uses 8 instances, the proposed one. GANDAFL is using 3.
Exactly. When fitting in 8 instances, I do have some reduction in the frequency. So it's not like it scales linearly or something.
Okay.
So now the next experiment actually is what you asked me before. So I checked this multi-accelerator design for 3 different data sets, and I customize the architecture to each of those. For all of these cases, again, I managed to fit up to 8 accelerators. So for the simulated data sets, I have 5 accelerators that support up to 1 edit, one that support up to 2, one up to 10, and one up to 18. So you can see that there's a very similar actually distribution for the edits, but I have used a different one for each data set. And by comparing the integration with Bot-I2 and comparing with my previous solution, I get almost 2 times speed up by using these lighter sized accelerators while retaining my accuracy.
Do you know why you're losing from the accuracy? Is it sneaky snake?
Sorry, what do you mean that I'm losing? I get the same as the reference at this point. But it's kind of tricky.
So you have 98.9 alignment rate.
Yeah, I lose some of the alignments, but the overall score remains the same somehow here. And I have attributed to the fact that it's not in the reported ones. I'm missing some of the non-reported alignments. But sorry, can you repeat the question?
I guess so. Then maybe have you checked your false negatives? Maybe I could
Okay, with sneaky snake.
modify my
Okay.
question, yeah. And false positives and false negatives, let's say. Maybe somehow you have different numbers over there.
So for like for an edit threshold more than 10, I saw that the integration with the sneaky snake actually got the same alignment rate as the reference one. So even though I stop at 18 here, I get the same percentage. But if I were to look into each alignment one by one, maybe I would discover what you mentioned.
That's what I was thinking is there's positiveness in snake, right? I guess, which means.
So maybe this would keep my percentage the same, but essentially I would. Okay.
Exactly. So it says the read should align, but it's not aligning, meaning there are more edits than it predicts. And you still, I guess, use the accelerator with lower edits, right? Because this is what sneaky snake is telling you. And in that case, maybe you're not aligning just basically because of that. Or maybe that's causing some issues.
And how would I detect that?
I would probably simply look at the multi output and then exactly as you said, 1-to-1 comparison.
Okay.
Whether you're outputting it or not.
So maybe like develop some sort of scripts that automatically infers somehow the differences.
Exactly. I mean, in the worst case, I would simply use, let's say, more sensitive accelerator. So
increase the threshold.
Exactly, rather than completely relying on sneaky snake output. For example, sneaky snake says 3, you could simply use 5.
Oh, okay.
Just
to be safe.
I mean, if accuracy is important.
Okay, very interesting. So actually this concludes also the second framework, and this is the summary of the works I presented. So the first one is the data flow acceleration for Smith-Waterman, and highlights both the data flow computing model as well as the integration-aware hardware-software co-design. And the second one is this profile-driven banded Smith-Waterman acceleration, that highlights the merit of actually exploiting some input characteristics in order to create a system of multiple accelerators, heterogeneous one with another, that can deliver in total higher throughput.
Sorry, when do you use the high-level synthesis to design the whole system?
I use it because this data flow computing model is actually based on a programming model available by MicroLab. This is a company, and it's sort of something like a Java language. So I don't program it this in HDL language. So it's a Java-like thing that inside the compiler transforms it into HDL, sort of like HLS does.
So you choose that because of constraint of using a specific framework?
Yes, there was a constraint in the project I was involved.
Is it also possible to use this profile-driven approach like a real-time system? For example, depending on the data sets, now we have different accelerator choice, like design choices, right? So can we, for example, use this in very different data sets, like a whole pipeline system, and then depending on the data set, can we have, let's say, elastic or changing designs?
Actually, I was hoping for that with the case. It's one of my future works that I would like to accomplish that. I think it's very hard to do, but it would be very interesting to do that and manage to have a different input and have several different architectures on the FPGA, and in the runtime decide with some smart and sophisticated, let's say, algorithm, which one should go where, and without compromising greatly on the accuracy and the acceleration. Okay, so lastly, this is some of my ideas for future work and some new research. So the first one has to do exactly with, or similar to what you mentioned. I would really like to further explore how the input sensitivity can impact an application, and in turn the accelerated architectures for this application. So I find it very interesting to study the impact of the input on the application and the different behaviors, and then propose a sort of data-driven approach to build a resource-efficient, high-throughput system that can support multiple functionalities. And then I move on to some, actually, I'm not sure if there is time. I have prepared some slides for these ideas.
We have time.
Okay. Okay, so then let's move on to the next one. So this idea sort of contemplates the fact that the input can impact, if it's different, it can cause the application to operate differently in terms of computation, functionality, and resources. So this use of generic accelerators would most likely lead to some over provisioning of resources. So what I would suggest here is to find some framework that employs a data-driven approach, finds any possible sources of variance within the input and the impact that this can have on the design, and then use some customized multiple heterogeneous accelerators. So the goal here, for example, is to see how the read length and the error rate can actually affect the accelerator size, or they can even enable different execution paths within the application that would correspond and translate to different accelerators completely. And also it would be very interesting to find let's say, the frequency and the percentage in which these inputs occur, so that we can also then modify how these accelerators balance one with another. So I believe that this would lead to a very interesting co-design approach between the accelerators and some exploration to find the best configuration for any given input. Okay, so this is one of my research ideas. Another one has to do with moving on from only targeting the read alignment, but also expanding the optimization to the other stages of genomic pipelines. So I would consider end-to-end optimization of genome analysis. However, on a platform that also takes into account the requirements of each step. So we can see that the genome analysis is bottlenecked by many diverse stages. Each one has its own bottleneck. For example, the seeding is bottlenecked by the search queries and the frequent accesses to the memory. The read alignment is bottlenecked by these string matching operations. And the latest variant callers use some deep learning models to perform the variant calling. Of course, we have to take into account that there is a very heavy data movement between those stages. So what would be ideal is to accelerate the end-to-end genome analysis by targeting the steps individually as well as in synergy. And ideally, this would happen on a single application platform that would also take into account the requirements for each step. So the platform that I would have in mind would be one that combines multiple features, for example, programming logic for the accelerators, the ability to let's say, change the memory layout, how is best suited for the accelerators, some AI cores that are most suited for accelerating the deep learning and other DNN operations in other steps of the genome analysis. And this also be coupled with some really fast interconnect for fast data propagation, and also have access to some high bandwidth memory in terms of capacity and reducing the latency. So what I had in mind and how this idea actually occurred is by taking the opportunity of this Xilinx Versal series and that combine many of these features together. And I would consider that they would be for a great prototype to examine how these separate stages and accelerators for each stage could interfere one with another in terms of sizing, scalability, sharing the resources, and potentially reach an optimal configuration for this architecture that can later on be also transferred in another platform more efficient. For example, this really reminds me of GenPip and how everything is coupled close together in memory.
Sorry, in this case, realignment and seeding, they are not implemented as a in-memory acceleration, right?
No, no. That would be like a typical FPGA accelerators that I have encountered.
Where do we run this end-to-end?
The end-to-end is because I don't only focus on the read alignment, but also now add the seeding and the variant calling steps, for example.
Yeah, but I meant like this end-to-end like processing. Do we run it today on a real computer? With one computer? Or... I'm asking both.
Oh.
I'm looking at John, but I'm asking everyone.
You mean like without
Yes.
an accelerator,
Genomic
using
mix.
software only? So
Yeah, exactly. Do you have like one machine that does all four of these today?
you can, yes.
GATK has pipeline, so it has like different steps, but at the end of the day, you can run it on a cluster if you have a big, let's say, big data set. You can run it on a cluster, but you can also run it on your, let's say, customized computers. But in most cases, GATK offers different sub-steps for the researchers, let's say, but for each and every step, there are also other alternatives in the literature that people can go for.
And are we sure like data movement is currently the bottleneck, but not an individual step?
I think all of these attribute to the overall bottleneck. But there's definitely, I understand that there is an intense data movement, and also in some accelerated solutions, for example, if you utilize a hardware accelerator for the read alignment, and then you would place this on the FPGA, then you create even more data movement between the host and the accelerator. So in the end, you would like to have all of them on a platform to at least eliminate this bottleneck and also target the individual, let's say, bottlenecks in each of these steps.
So that's a similar motivation you have, Jansto, right? So you're Jansto, so you're designing hardware accelerators. Okay, so you're solving some performance related issues, but then the data movement part is now getting more important. You need to solve as well. Design accelerators.
Yeah.
But how much, how big a problem it is, I guess it depends on the application and I guess that also, so.
But I think she was referring to data movement that we have. So when we have different accelerators for different steps, we may have some extra data movement across them, right?
Actually, in this figure, I was mentioning the original data movement that exists naturally because one fits the other. But as a motivation for actually using the same platform, I also mentioned exactly what you said,
Yeah,
that it gets worse.
Next further comment.
So part of application is running on CPU, the other part accelerator. There could be some, I don't know, extra data movement because of what?
So isn't the worst case it goes first to disk and then?
Yeah.
Okay.
So I guess then how SSDs play a role here in this picture. Did you think about it? I mean, we discussed it a bit. in our
Yeah.
meeting, but-
So I guess this HBM would be useful if it existed to store a
And if it is
large
large
data.
enough. I guess.
Yeah, but I guess it's never large enough, so I'm not sure.
I was gonna say, if you have, so the access patterns, is it something that's very random, unpredictable, or do you stream through things? So you might need large storage, but maybe, I mean, these are very simple questions. If you
I
have
didn't
such
understand
a
the question.
simple streaming access pattern, basically you can have enough throughput to feed
Yeah.
your.
So unfortunately, it's not always the case. For example, in variant calling, you need to first almost completely finish the read alignment part,
Yeah.
then start variant calling because you need like some collective information. Or maybe that could be like some, I don't know.
We could
Like-
find maybe some
on the
minimum
fly.
batch size for that.
Maybe, or on the fly consensus calculation or something for variant calling. And as you have new alignments, you update that consensus, I guess, knowledge you may have so that you don't have to.
That
explain.
looks like
That
them.
would be nice. Is there an algorithm? Progressive,
Not to my knowledge, yeah, that could be interesting, actually.
because currently we should do read alignment for all reads,
Yes,
get it done and then go to the
yes, and there's basically some data processing in between.
So essentially
Some
there is
cleanup.
no much pipeline here, no? We need to get it done fully and then.
Exactly, and even after alignment, you have this cleanup, like some sorting and you remove some duplicates and matches and so on.
Yeah, I think that progressive is nice.
Are there, I don't think there are such websites, are there any, have you checked that? Like some, let's say, progressive variant calling, let's call it that.
Nothing comes to mind. I haven't really worked with variant callers in this depth,
Okay.
to be honest.
I have something to say here. So basically, do you consider like the how to say the utilization of the accelerators? For example, you can utilize the AI ML engines for both the base calling and the variant calling. And then, for example, you can also utilize some accelerators for the, let's say you have some unique operations such as string matching operations. Then you can utilize the, because when you do the, for example, you do the, after you finish the base calling, you actually, sometimes you don't need that accelerator, then you can utilize it for the other, let's say,
So if I understood correctly, you mean that I could leverage these AI engines from the variant calling, and when it's not utilized, use it from the base call?
yes. So we
Yes,
can
that's
also-
interesting. Yeah.
So it's just an example. We can also like extract some common operations inside this pipeline, and then make the accelerators more compact, let's say, for the whole procedure. So you can design, let's say, accelerator for the string matching and accelerator for the, let's say, vector matrix multiplication, and the accelerator for the, let's say, other basic operations that you can, common operations that you can find in this whole pipeline. Then you can utilize them as much as possible, and then also you can design the accelerators more in a more compact way.
So for example, have like an accelerator that can be used for the alignment and the chaining, and maybe.
Yeah, exactly. Otherwise, you have, for example, once you finish maybe the city and grid alignment, those resources, those accelerators are like idle there when you do the other operations.
I was actually thinking that maybe all this could be some sort of streaming operations. So in that case, I would have more reads incoming. However, Jan just mentioned that for the variant calling, you have to first finish with the, which I didn't have that in mind, to be honest. I didn't know.
But that's the standard approach, right? If you could somehow design a new algorithm that dynamically builds some consensus as the new alignments
Yeah,
come in,
maybe.
you could still stream, I guess.
Or maybe in variant calling, you would need like the information from all the data set. The entire
Ideally,
one.
yes.
Okay. I
I
was
mean, for a
wondering
position, let's say
if you do some sort of windowing approach, and then the consensus you mentioned, maybe something like that.
maybe, or like you have consensus for every position and you keep somehow updating that consensus.
Okay. Yeah. But this, let's say, sharing of resources, I think it's very interesting to see in this tightly coupled architectures, definitely.
It also depends on, I guess, the throughput at each step, right? By some chance, the throughputs are relatively the same. Yeah.
Also, this could be part of the exploration to
Exactly.
give more resources to match the throughput and don't have any sort of stalling operations.
Exactly. So I guess some flash processing could also, yeah, make it done.
So we are running the replay.
Okay. Okay, this is it actually. The other one, it's really, I think, it's serverless genomics, which is kind of outside maybe the scope of this discussion, I guess. And the idea was to accelerate a genomic pipeline by making a convergence of cloud capabilities, serverless, as well as accelerators. In principle, it's similar to the previous accelerator architecture, because again, I would recommend to actually find different ways to perform the stages, different threads, different sizes, and run it on different nodes based on the needs of the pipeline.
It actually goes against the previous idea, right? This will increase data movement a lot, probably.
Well, in my mind, it could be true. I was thinking that maybe because I would overlap these computations, and as soon as the data are consumed, are produced, they're consumed. But I guess this is not the case.
And to do that, you need to do it in the same machine, or maybe even in the same chip.
Yes, I was talking, I'm not sure who, because I talked this idea for many of the group members. And they mentioned that there could be some, let's say, that placement, scheduling a placement of these stages, maybe on the same node to have access to the data. But again, I think it was it's a, so.
Yeah, I was discussing.
Yeah.
Oh, the function program function is weak.
But this is it from me. Thank you very much. Thank you for listening to me.
Any question on YouTube? Okay.
Shall I
Thanks a
end
lot.
the meeting? Oh, thanks.
Thanks a lot.